What makes a machine intelligent? That's the question and problem that sits at the core of all of machine learning, all of artificial intelligence today. In this video, I'll cover everything there is to know about it. Can machines think? To the Turing test, to the Chinese room argument, to thoughts and actions, and to the mathematical connection to it, empirical risk minimization. So let's start with the question that started it all, from Alan Turing. Can machines think? It's a very, very simple question, but it carries deep meaning and deep weight, because it's what started the entire AI revolution. Often this question is very vague. While it's philosophically stimulating, how do you actually quantify this or define this in practice? So he took it a step further and proposed a practical thought experiment called the imitation game. How it works is, imagine you are a police detective. In front of you is one criminal and one citizen. Your job is to find out who the criminal is and who the citizen is, but you don't know which one is which. The criminal's goal is to trick you into thinking that they are the citizen. They're trying to fool you into thinking that. The citizen's goal is to tell you the truth. And while there are two goals, your goal is to determine whether the criminal is the same as the citizen and differentiate between the two. If you can't tell who is who, then the criminal can be classified as intelligent. If it's very, very obvious that the criminal is not a good person and is evil, then the criminal isn't classified as intelligent. Now replace that concept with a machine. Instead of having a criminal and a civilian, have a machine and a human. A machine tries to imitate or copy the human as well as possible. If you can't tell the difference, if you can't tell which one is the machine and which one's the human, then the machine imitates well and it's intelligent. But if it's very obvious, then the machine is unintelligent. Do you think this sounds plausible? Is it accurate? Well, it was a breakthrough for its time. But there was one argument called the Chinese room argument that caused significant debate. So the fundamental question that the Chinese room argument asks is imitation, does that count as intelligence? And does what we see from the outside match what is going in from the inside? To understand this better, imagine there is a non-Chinese speaking individual in a room and his boss wants to test his Chinese. So instead, he passes notes of Chinese characters into the room in which the guy in the room has to try and translate these Chinese things into English. However, he doesn't know any Chinese. What he does have, however, is in the same room is a textbook of all the Chinese definitions and all the terms he needs, basically like a lookup dictionary, the answer sheet. So instead of doing it himself, he can just take a look at the question and then go onto the book and just check it. But from the outside of the room, he gets 100%. And to the boss, it looks like that he understood all of it. He understands and knows all this. But does he really? No, he was just copying and pasting without understanding the true meaning. So the connection to the Turing test is that the Chinese room argument states that what we see from the outside doesn't always mean what we're going on from the inside. The machine that imitates the human very well, or classified as intelligent by the imitation game, could just be copying, not actually learning and being actually intelligent. It could be just copy and pasting these without actually understanding. So it doesn't actually understand the pattern. It just understands the raw thing. And to understand this question better, we have to contrast thoughts versus actions. Thoughts are on the level of parameters, like your internal knobs, and actions are on the level of functions, or what you actually output or what you actually do. And the key distinction is that thoughts are never or rarely the same as actions. What you see with someone doing something does not always match what they're thinking about. So, what's better? A machine that thinks smart or a machine that acts smart? It's about uh, parameters versus functions. And in a Turing test, we consider how they act smart. The machine has to replicate the human as well as possible. And from the outside point of view, it seems very intelligent. But the Chinese room argument asks, does it think smart? Internally, does it actually understand it, or is it just appearing so to the outside world? So it's about what we can see and what we can't see. And that's the idea behind AI interpretability. Most machines today are black boxes, which is why we want to sometimes understand the thoughts behind them on the level of the parameters, not just their outputs, which we can see whenever we prompt an AI. The key interpretability dilemma is this. The Turing test sees intelligent functionally, or what it is on the outside, and the Chinese room argument sees it parametrically, or what it is on the, I should say inside. But what is better? That's the fundamental question of machine learning. Would it be better to have an AI that acts intelligently or an AI that thinks intelligently? Let's add some mathematics to it. Recall from the last video how we mentioned empirical risk and expected risk. So what we want to minimize is the expected risk, or the expectation, the left hand side formula. This is the risk for the infinitely large data set. But unfortunately, we cannot access this because we don't have access to the full, true nature or the data generating process. It's completely unknown to us. For as much as we want to understand the entire universe, we can only access a small sample of it, which is our data set. And this sample, we hope, is representative, a proxy to understanding the full thing. So instead, we use another objective called empirical risk minimization. We minimize the right-hand side formula, which is just minimizing the empirical risk, or the average loss across all data points in the finitely large data set we have. So we can, to summarize, we want to minimize the left-hand side, which is the expected risk, but the only way we can do that is to do the right-hand side, which is the empirical risk. So it's about what we can do and what we want to do but can't do. An interesting finding is the strong law of large numbers, and it states that as the data set size n grows larger and larger, or as it approaches infinity, the empirical risk actually approaches the expected risk. And if you have an infinitely large data set, then the empirical risk is the expected risk. If you have, but obviously we can't have an infinitely large data set. That would require accessing the entire true unknown nature data generating process. So we can see that more is obviously better. More data is, generally speaking, it produces much, much better results. There's more of variety. And because empirical risk goes towards or approaches expected risk as n goes to infinity, this yields better generalization, because the end goal is to obviously minimize the expected risk. We can see that the formula describes this phenomenon. The limit as this dataset size n goes to infinity or grows larger of the empirical risk is the expected risk. What is it is essentially saying is, as the dataset size grows larger, the value that the empirical risk approaches is the expected risk. The empirical minimizer is the function or model that makes the empirical risk as small as possible. So it's the best possible one for this specific data set. It's the one that makes the empirical risk the smallest out of like all possible models on that specific data set. The oracle model is the function or model that makes the true expected risk the smallest. Obviously, we can't access this one because we can't access the true distribution. But it's a hypothetical optimal model, and it's what we want to seek, but it's often very impossible to guarantee in practice. The relationship is this. The expected risk or true risk of the optimal oracle model is always smaller than or equal to the one of the empirical minimizer. And the empirical minimizer's empirical risk is always smaller than or equal to that of the oracle model. This is true by the definition of the empirical risk and the oracle model. As the oracle model is the best one on the data, the true distribution, the full infinite data set, while the empirical minimizer is the best one on the sampled data set. So how do we bring this back to our question? Learning syntax is like memorization, which is like empirical risk minimization. Imagine like you're learning the times tables. Learning syntax would be memorizing the timetables rules. You don't actually like understand that. That would be learning syntax. But does it generalize beyond that? If you're just memorizing it, can you apply this to new scenarios where you haven't memorized it, to unseen data? Not always, which is why empirical risk minimization is like a proxy to get to the what we truly want, which is generalization. Learning semantics is like generalization, or minimizing the true risk. And the optimal semantics model is thus the oracle model. This is what we want to achieve. And it's like, instead of memorizing the times tables, if you're learning semantics, you'll be learning the concept of multiplication itself, so that you can apply it to new scenarios and unseen data, even when you haven't memorized the timetables. So it's about learning a pattern, not about learning just specific examples of it. The connection between the Turing test and what we have talked about. The interpretability contrasts internal and external intelligence, what we can see from the inside and what we can see from the outside, and that they're always or usually different. About how a model's output, what we can see, and what the actual model does, can be very, very different from what the model is thinking about. And because of this interpretability dilemma, where what we see on the outside is not always what we see from the inside, the fundamental question that the Chinese room argument asks is, how do we know whether our model is a syntax model or a semantics model? How do we know whether it just memorized it or generalized it? Is it, did it generalize well? Because what often happens is from the outside, from the functional point of view, the action, syntax, or empirical risk can appear externally identical to semantics. So that leaves us a thought-provoking question. What really is intelligence if we don't know which one is which?